Algorithmic complexity is a big idea in computer science. It sounds a bit fancy, but it is really about understanding how much work a computer has to do to solve a problem. Think of it like this. You have a task, and you have different ways or recipes to get it done. Some recipes are quick and easy, others take a lot of time or need many ingredients. Algorithmic complexity helps us figure out which recipe is better, not just for a small job, but especially for really big jobs. It is not about how fast your computer is, like how many gigahertz its processor has. That is important, sure, but algorithmic complexity looks deeper. It asks how efficient is the method itself. Is the way you told the computer to do something a smart way, or is it a really roundabout, slow way? This distinction is key. A super fast computer running a bad method will still be slower than a pretty good computer running a smart method, especially when the problem gets big. We mostly talk about two main things when we think about complexity, time and space. Time complexity is about how long an algorithm takes to run. Space complexity is about how much memory it needs. Most of the time when people say algorithmic complexity, they are thinking about time complexity. It is often the bigger concern. Let us start with time complexity. Imagine you have a list of 1,000 names, and you need to find one specific name. How would you do it? One way is to start at the top and look at each name, one by one, until you find the one you want. This is a very simple method. If the name you are looking for is the very first one, you get lucky and it is super fast. If it is the last one, or not there at all, you have to look at all 1,000 names. Now, what if you had 10,000 names? Or 100,000? With this one-by-one method, if the number of names doubles, the time it takes to search could also roughly double. If it triples, the time roughly triples. This kind of relationship is called linear. The time grows in a straight line with the size of the input. We have a special way to describe this called big O notation. For our one-by-one search, we would say it is on. That stands for the number of items in your list. So, on means the time grows linearly with and. But wait, there is a better way to find a name in a big list, right? If the list of names is sorted, like in a phone book, you do not look one by one. You probably open the book somewhere in the middle. If the name you see is too early alphabetically, you know the name you want must be in the second half. If it is too late, it is in the first half. You then take that half and do the same thing, open it in the middle again. You keep cutting the search space in half. This is called binary search. Binary search is much, much faster. If you have a list of 1,000 names, you might need maybe 10 or 12 checks to find the name. If you have 1,000,000 names, you might only need about 20 checks. Think about that difference. One method takes 1,000,000 steps, the other takes 20. This kind of method, where you keep having the problem, is called logarithmic time. We write it as all log and log and grows really, really slowly as it gets big. It is one of the best kinds of complexity you can hope for. So, big O notation is just a way to classify algorithms. It tells you how the performance of an algorithm changes as the size of the input data changes. It does not tell you the exact time in seconds, because that depends on your computer, what else is running, and many small details. Instead, it gives you a high-level idea of the algorithm's growth rate. It is like saying, this car is fuel efficient for long trips, versus this car drinks gas like crazy. You are not talking about exact miles per gallon, but giving a general sense of its efficiency for a specific use. We usually care about the worst case scenario when we talk about big OY, because the worst case gives you a guarantee. You want to know, what is the absolute longest this thing could take? If your search algorithm is on, the worst case is you have to look at every single item. Maybe the item is at the end, or it is not there at all. If your search is olog nen, the worst case is still very fast, because you are constantly cutting down the problem size. Let us look at some common big O categories from best to worst. First, there is un. This is constant time. It means the algorithm always takes the same amount of time, no matter how big the input is. It is like asking for the first item in a list. You do not care if the list has one item or 1,000,000,000 items. Getting the first item is always one step. It is super efficient. Then comes log(n), which we just talked about, logarithmic time. This is excellent for large data sets. Binary search is the classic example. Next up is on. Linear time. Our one-by-one search is an on algorithm. If you have to do something once for each item in your input, it is likely on. For example, if you need to print every name in a list, you have to go through each name, so it is on. A bit slower is on log(n). This is often called linearithmic. Many good sorting algorithms fall into this category, like merge sort or quick sort. As they are faster than on for searching because they do more work per item, but they are still much, much better than the really slow ones. It means for in items, you are doing roughly in steps, but each step involves a logarithmic search or operation. Then we hit on raised to the power of 2. This is quadratic time. It means the time grows with the square of the input size. If your input doubles, the time quadruples. If your input triples, the time becomes 9 times longer. This happens a lot when you have nested loops. Imagine you have a list of names, and for every name, you need to compare it to every other name in the list. That will be on raised to the power of 2. Simple sorting methods like bubble sort are often on raised to the power of 2. For small lists, it is not a big deal. For a list of 1,000,000 items, on raised to the power of 2 means 1,000,000 times 1,000,000 operations, which is 1,000,000,000,000. That is going to take a very long time. It gets worse. Much worse. There is Otwo raised to the power of n. This is exponential time. If your input size increases by just 1, the time it takes roughly doubles. If n is 10, it is 1024 operations. If n is 20, it is over 1,000,000 operations. If n is 30, it is over 1,000,000,000. Algorithms with this complexity are typically only useful for very, very small inputs. They usually involve trying every possible combination or subset of the input, and finally the really scary one, on. That is factorial time. This grows incredibly fast. If n is 5, it is 120. If nn is 10, it is over 3.6 million. If n is 20, it is something like 2.4 quintillion. You almost never want an algorithm with this kind of complexity, unless n is tiny, like 4 or 5. It often pops up in problems where you are trying to find every possible ordering of a set of items, like the traveling salesperson problem in its brute force form. Understanding these categories is important because it helps you predict how your software will behave as the amount of data it handles grows. If you are building something that needs to scale to millions or billions of users or data points, an on raised to the power of 2 or Otwo raised to the power of n algorithm is a non-starter. You need something in the O log n on or on log n range. Now let us talk about space complexity. This is similar to time complexity, but instead of tracking operations, we track how much memory RAM an algorithm needs. Just like time, we express it using big O notation, and it also depends on the size of the input. For example, if you have a list of 1,000 names and you need to store a copy of that entire list in memory, then your space complexity is on. Because if the list doubles in size, the memory you need to store the copy also doubles. But what if your algorithm only needs a few variables to do its work, no matter how big the input list is? Maybe it just keeps track of the current name it is looking at and a counter. In that case, the amount of memory it uses does not really grow with the input size. It stays pretty much constant. That would be space complexity. Sometimes there is a trade-off between time and space. You might be able to make an algorithm run faster by using more memory. For instance, you could pre-calculate and store a bunch of results in a big table using more space so that you can look them up instantly, later saving time. Or you might sacrifice some speed to use less memory, which is important on devices with limited resources. When we talk about big O, we mostly focus on the dominant term. What does that mean? Well, if an algorithm has a complexity of on raised to the power of 2 plus n, we just say it is on raised to the power of 2. Why? It's because as n gets very, very large, then raised to the power of 2 part grows so much faster than the as n part that the n part basically becomes irrelevant. Imagine n is 1,000,000. N raised to the power of 2 is 1,000,000,000. N is just a tiny fraction of that. So, we simplify to the biggest factor. Also, big O notation ignores constant factors. If an algorithm takes 5n steps, we still call it on. If another algorithm takes 100 steps, it is also on. This might seem weird because 100 is clearly slower than 5n. And it is, but big O is about the growth rate, not the exact number of operations. Both 5n and 100 grow linearly. If n gets large enough, eventually the 5n algorithm will be faster than some on log n algorithm, but they are in the same general class of linear growth. The constant factors do matter in real-world performance for smaller inputs, but for very large inputs, the big O category is the most important indicator. Let us think about this constant factor idea a bit more. Imagine you have 2 cars. One car is an old beat-up sedan, but it is super efficient on the highway. We will say its efficiency is on for a long trip. The other car is a fancy sports car, but it needs to stop for gas every few miles. And its efficiency might technically be on log n because of some smart engine design, but those constant stops make it slower for short trips. For a very long trip, though, the sports car will eventually pull ahead because its fundamental growth rate is better. Algorithmic complexity is like understanding that fundamental growth rate. For small tasks, the beat up sedan a less optimal Big O, but with small constant factors might even be faster. But as the task scales up, the sports car better Big O will win every time. So, when does this really matter? It matters when you are building software that needs to handle real-world data sizes. If you are writing a script for yourself to process 10 files, an on raised to the power of 2 algorithm might run in a blink. Who cares? But if you are building a social media platform that has to process millions of posts per second, choosing an on raised to the power of 2 algorithm for a core feature could crash your entire system or cost a fortune in servers. This understanding helps software engineers make informed decisions. Should I use this sorting method or that one? How will my database queries perform if the number of users doubles? Can my system handle a sudden surge in data? Algorithmic complexity gives you the tools to answer these questions with a good degree of confidence. It is not about writing code that is fast enough for today, but writing code that will still be fast enough tomorrow when the scale of the problem is much larger. Let us dig a bit deeper into some practical examples. Searching. We already covered linear search on and binary search, O log n. The key difference is whether the data is sorted. If it is not sorted, you have no choice but to check potentially every item. If it is sorted, you can use binary search and dramatically cut down the search time. This shows how the structure of your data can directly impact the complexity of your algorithms. Sorting is a classic computer science problem. Simple sorting algorithms like bubble sort or selection sort are typically on raised to the power of 2. They work by repeatedly stepping through the list, comparing adjacent elements and swapping them, or finding the smallest element and putting it in place. For a list of 100 items, this means around 10,000 operations. For 1000 items, a million. More advanced sorting algorithms like merge sort or quick sort are on log n. For 100 items, this is about 100 log 100, which is roughly 107 OA 700 operations. For 1000 items, it is about 1000 locked in 100, which is roughly 10,000 operations. You can see how much better on log n is compared to on raised to the power of 2 as it grows. The difference becomes massive. What about data structures? The way you organize your data also heavily influences complexity. If you need to quickly look up an item based on a key like finding a person's phone number by their name, a hash table or dictionary map in many programming languages can often do this in OON time on average. It is like having a direct address for each piece of information, but if you store that information in a simple list, finding a person's phone number by their name would be on because you would have to search through the list. If you need to quickly add or remove items from the beginning of a list, a linked list might do this in OON time. But in a regular array-based list, adding or removing at the beginning might be on because all the other items have to be shifted. So, choosing the right data structure for your specific needs is a huge part of writing efficient code. It is not just about the algorithm, it is about how the data is stored to support that algorithm. Let us talk about how you actually figure out complexity when you are looking at code, or even just thinking about a problem. The most common things that drive up complexity are loops. If you have a single loop that runs in times where n is the size of your input, that is usually on. If you have 2 nested loops where the inner loop runs in times for each iteration of the outer loop, which also runs in times, then that is on raised to the power of 2. 3 nested loops on raised to the power of 3. A loop that always runs a fixed number of times, say 5 times, no matter the input size. That part is OON. Function calls matter too. If you call a function inside a loop, you need to factor in the complexity of that function. If the loop is on and the function call is on, then the total complexity for that section becomes on n, which is on raised to the power of 2. Recursion can be a bit trickier to analyze. A recursive function is one that calls itself. If it calls itself n times, and each call does constant work, it might be on. But if it calls itself multiple times within each call, like a function that calculates Fibonacci numbers in a naive way, where fib calls fibin1 and fibin2, that can lead to exponential complexity, otwo raised to the power of n, because the number of calls doubles roughly with each step. It is really a mindset. When you are designing an algorithm or writing code, you should always be thinking, how many times will this operation run? And how does that number change if my input gets bigger? Sometimes you might hear about best case and average case complexity, not just worst case. Best case is the most optimistic scenario. For linear search, the best case is OON if the item you are looking for is the very first one. But this is not usually very useful for planning because you cannot count on it. Average case complexity is how the algorithm performs on a typical or random input. This can be more realistic for some algorithms. For example, quicksort has a worst case of on raised to the power of 2, but an average case of on log n, which is why it is often very fast in practice. But because the worst case can happen even if rarely, engineers usually design systems to handle that worst case, or they make sure the worst case is practically impossible, like by picking good pivot elements in quicksort. A common misconception is that Big O is only for big data. While its advantages are most pronounced with large inputs, understanding complexity is good practice even for small problems. It trains your mind to think efficiently, and small problems can grow. Today's 100 items might be tomorrow's 100 million. Another misconception is that the algorithm with the best Big O is always the fastest. As mentioned earlier, for small inputs, an algorithm with a worse Big O but with very small constant factors might actually be faster than one with a better Big O but higher constant factors. For example, a simple on raised to the power of 2 sort might be faster than a complex on log n sort for a list of 10 items because the on log n algorithm has more setup and overhead instructions. But as the list grows to 1,000 items, the on log n algorithm will quickly overtake and dominate in speed. You generally optimize for the typical scale of your problem. Why is all this not just theoretical university stuff? It directly impacts user experience. Nobody likes a slow app or a website that freezes. Fast, responsive software is often the result of smart algorithmic choices. It impacts costs. If your code is inefficient, you need more powerful servers or more servers to handle the same workload. That means higher electricity bills, more hardware to buy, and more maintenance. Efficient algorithms save money. It allows for scalability. If you build your system with efficient algorithms, it can handle more users or more data without needing a complete rewrite or a massive hardware upgrade. This is vital for any successful product. And yes, it is a common topic in technical interviews, where companies want to hire engineers who can not only write code that works, but code that works well and efficiently. So, how do you get good at this? Practice. Look at code you write, or code you see, and try to identify the Big O complexity. Break down problems. If a problem seems complex, break it into smaller parts. Analyze each part. The overall complexity will often be dominated by the most expensive part. Learn common algorithms and data structures. Knowing how a hash map works or how merge sort works gives you a toolbox of efficient approaches. Do not optimize prematurely. It is a good idea to think about complexity from the start, but sometimes a simple, clear-on solution is perfectly fine if and will never get large. Do not spend days optimizing something to O log n if and will only ever be 5. Focus your optimization efforts where they will make the biggest impact. Profile your code if you suspect a bottleneck. Sometimes the slow part is not what you expect. Algorithmic complexity is a foundational concept in computer science. It is not just about memorizing formulas. It is a way of thinking about problems and solutions. It is about understanding the fundamental properties of different approaches to solving a task. It helps you design software that is not just functional, but also robust, scalable, and performant. It is a skill that empowers you to build better systems and make smarter technical decisions. It helps you distinguish between a temporary fix that works for small inputs and a truly sustainable solution that can handle the real world's ever-growing demands.